Welcome. In this session, we'll talk about complex numbers. Now, the first question here is why we need to study complex numbers in electric circuits. Now, the answer is because the next topic, that is the phasor analysis, is based on the idea of complex numbers. Actually, a phasor is a complex number. Phasor is simply a complex number. That's our next topic. So in this session, what we'll do, we'll learn how do we represent a complex number and how do we perform different operations on these complex numbers. So let's start with how we represent a complex number. Okay, so let's talk about the representation of this complex number. First representation of this complex number is called the rectangle form, and in rectangle form we write the complex number as a plus j b. So this is called the rectangular form of this complex number. Okay, where a is called the real part of this complex number and b is called the imaginary part of this complex number, and j, which is same as iota in mathematics class, is given by under root of minus 1. Okay, so this is how we represent a complex number in this rectangular form. For example, we say z is a complex number and the real part of this complex number is 3 and imaginary part of this complex number is 4. So this is a complex number where a is 3, b is 4. How do we graphically represent this complex number? Graphically, we can draw this on a complex plane. On a complex plane, we have two axes, real axis and imaginary axis. So this is our real axis and this is our imaginary axis. Imaginary axis is also referred as geometry. So for example, if our real part of this complex number is a, and a is this much, and b, that is the imaginary part, is this. Okay, then we can say this is our z that's represented on this complex plane. So this is our complex plane. Okay, now what are the other forms of this complex number? Another form of this complex number is the polar form, and in polar form we write as z as r at an angle of theta, and this is referred as the polar form of this complex number. So this is the polar form of this complex number, where r is referred as the magnitude of this complex number. So r is the magnitude and theta is referred as the phase of this complex number. Okay, now what's the relationship of this polar form with the rectangular form? If you look at this graphical representation of this, and if we use the Pythagoras theorem, we know this will be b, and if we complete this triangle, okay, then this here will be r and this will be theta. So if you use Pythagoras theorem and there's Pythagoras theorem and trigonometric identities, we'll see r will be simply equal to under root of a square plus b square, and theta will be equal to tan inverse b by a. Okay, if you use Pythagoras theorem in this triangle a, b, and r, where r is the hypotenuse, b is the perpendicular, and a is the base, you will get r is equal to under root of a square plus b square. Similarly, theta will be equal to tan inverse b by a, because tan theta will be equal to b by a. So that means theta will be equal to. So this is the relationship of this rectangular form and polar form. Okay. So how do we convert a rectangular form? For example, this complex number, that is z is 3 plus 4j. How do we convert it into polar form? So we can convert it simply. We can write it as 3 square plus 4 square at an angle of tan inverse 4 by 3. Now 3 square plus 4 square is under root of 25, and under root of 25 is that is simply 5. So we can write it as 5 at an angle of tan inverse 4 by 3 is 53.13 degrees. Okay, please verify these. So we can convert this rectangular form to the polar form. Okay. Now, if we have to convert this polar form back to the rectangle form, now we have one more representation of this complex number. We can write z, that is given as r at an angle of theta, which is the polar form. We can write it as r e to the power of j theta. Now this is called the Euler's form. This is called the Euler's form, where r is again the magnitude and e to the power of j theta from Euler's identity can be written as cos theta plus j sin theta. And this is called the Euler's identity. This is the Euler's identity. Okay. So if we have to convert a polar form into rectangle form, how do we do that? We say z is equal to r e to the power of g theta. E to the power of g theta I can write as cosine theta plus j sine theta. So I can put as r cosine theta plus j plus j r sine theta. So this is the real part and this is the imaginary part. So this is how we convert a complex number in polar form to this rectangle form. So if rectangle form is given, so we can convert it into the polar form like this. R we can convert it into the polar form r at an angle of theta, where r is under root of a square plus b square, and theta is tan inverse b by a. Similarly, if the polar form is given r at an angle of theta, we can write it as r e to the power of j theta, can be written as r cosine theta plus j r sine of theta. This is our rectangle form. Okay, so we can convert one form to another form from these equations. So these will help us to convert the rectangle form from one form to another form. Okay. Next, what we'll do, let's learn the basic operations in this complex algebra, and what are the different operations that we perform on these complex numbers. So first, now let's talk about the operations. And the first operation that we'll talk about is the conjugate of a complex number. Conjugate of a complex number. Now, conjugate of a complex number, suppose the complex number is given in this rectangle form, which can be converted into polar form like this. So we can write it in the polar form or Euler's form like this. So the conjugate of this is simply written as z star is the conjugate. Simply replacing j by minus j in rectangular form will give you the conjugate, or if the polar form is given, simply replacing theta by minus theta will give you the complex number. R, we can write it as R e to the power of minus j theta. So this is the conjugate of this complex number. For example, the Abu complex number, that is z is equal to 3 plus 4j. 3 plus 4j can be written in polar form as 5 at an angle of 53.1 degrees, can also be written in Euler's form like this. So the conjugate of this complex number can simply be written as z star is equal to 3 minus 4j. Or if the polar form was given, so you can write it. If the polar form is given, we can write it as 5 minus 53.3 degrees, or 5 e to the power of minus j 53.1. Okay. Okay. So that's how we compute the conjugate of a complex number. Simply replacing j by minus j in rectangle form, or theta by minus theta in polar form or Euler's form will give a conjugate of this complex number. Okay. Now next, what we'll do, if we have to perform the addition between two complex numbers. So let's suppose we have to perform the addition operation between two complex numbers. Suppose the two complex numbers z1 is equal to a1 plus b1, which can be written in polar form as r1 at an angle of theta 1, or in Euler's form as like this, r1 theta 1. Similarly, another complex number is a2 plus j b2, which can be written in polar form like this, r2 e to the power of j theta 2, depending upon which of the form is given. So we can convert one form to another form. Now how we perform the addition? The addition is simply given as, now remember, addition is always preferred in rectangular form. Okay, so we can simply add the two complex numbers here like this, a2 plus jb2. So we can add the real part with real part. So it will be a1 plus a2 plus j b1 plus b2. Okay, taking j common from these two, so we'll get this. So adding the real part with real part and imaginary part with imaginary. Now, what if the polar form was given, not the rectangular form was given? So what you will do, you will convert this into the rectangular form first. How do we convert a polar form to rectangular form? By using this relationship. Okay, so that's how we convert a polar form to rectangular form, and then we can perform the addition. If polar form was, if directly rectangular form was given, you can do the addition like this. Okay, all right. Similarly, if we have to perform the subtraction operation between these two complex numbers. So z1, suppose z1 is a1 plus jb1, which can be written as r1 at an angle of theta 1, or r1 e to the power of j theta 1. Similarly, suppose z2 is a2 plus j b2, which can be written as r2 at an angle of theta 2, which is r2 e to the power of j theta 2. Now subtraction, that is, suppose z1 minus, we have to perform z1 minus z2, can be written simply as jp1. Again, subtraction is preferred in rectangular form. So we can write it as a1 minus a2 plus j b1 minus b2. What if the polar form is given? So what you will do, you will convert the polar form first to a rectangle form and then perform the subtraction. Okay. Okay. How? Okay, next is if we have to perform the multiplication operation. So suppose if the multiplication operation is we perform between two complex numbers. So suppose the complex numbers are a1 plus jb1, which can be written as r1 at an angle of theta1, which is same as r1 e to the power of j theta1. Similarly, z2 is a2 plus gb2, which can be written as r2 at an angle of theta2, which can be written as r2 e to the power of j theta2. Okay, so multiplication is becomes very easy in polar form or Euler form. For example, we have to perform z1 multiplied by z2. Now, if we use the Euler's form, we'll write r1 e to the power of j theta1 multiplied by r2 e to the power of j theta2. Now, r1 multiplied by r2 is r1 r2. Bases are same, powers will get added. So e to the power of j theta1 plus j theta2. We can write this as r1 r2 e to the power of j theta1 plus theta2, which can be written in the polar form as r1 r2 at an angle of theta1 plus theta2. So what we got here, so the if polar form is given, simply multiply the magnitudes and add the phases. That's what the result says. Multiplying the magnitudes and adding the phases will give us the magnitude. So what if this rectangle form is given? We can also do the multiplication in rectangle form. We can also do this in rectangle form. Okay, so suppose z1 multiplied by z2, we can write as a1 plus j b1, which is then a2 plus j b2. If you multiply first with a1, so it will be a1 a2 plus j a1 b2. Then if you multiply with j b1, so it will be a2 here is j also b2 b1 plus j and j square b1 multiplied by b2. Now j square here is -1, so we can write it a1 a2 plus, if I take j common, this is a1 b2 plus a2 b1 minus j square is -1, so it will be b1 minus b2. Let's write the real parts on one side and imaginary parts on like this. Okay, this is the multiplication. Now you can see multiplication is very easy and becomes very easy in polar form. Simply multiply the magnitude part and add the phases. Okay, here you have to do 4 multiplications, right? Then adding and subtraction operation as well. But if you have to multiply simply two complex numbers, it becomes easy in polar form. Simply multiply the magnitudes and add the phases. Okay, so multiplication is preferred in polar form. Now, similarly, suppose we have to perform the division operation between complex numbers. So if we have to perform the division operation, let's suppose the two complex numbers are z1, which is r1 e to the power of j theta1, which is same as r1 theta1, and suppose this is the rectangle form. Similarly, z2 is r2 e to the power of j theta2, which is same as r2 at an angle of theta2, can be written as suppose a2 plus j bit. Okay, you can convert one form into another form as shown above. Okay, so what we'll do, we'll perform the division. So let's suppose we have to perform z1 divided by Z2. Now division is again preferred in Euler's form or polar form. So what we'll do R1 e to the power of j theta 1 divided by R2 e to the power of j theta 2, which can be written as R1 divided by R2 e to the power of j theta 1 into e to the power of minus j theta 2, because it is plus here. So on numerator side, this will be minus j theta 2. So we can write it as R1, R2 e to the power, bases are same, powers will get added. Okay, so this is the Euler's form of this division operation, so which can be written as R1 divided by R2 at an angle of theta 1 minus theta 2 in polar form. So again, division becomes very easy in polar form or Euler's form. Simply what we do, we divide the magnitudes and subtract the phases. Okay, in the multiplication, we multiply the magnitudes and add the phases. Okay, that's how we perform the division. We can also do the division in rectangle form, but it will be slightly there will be more calculations involved, because then we have to do rationalization. I will not do that part, so we'll leave it here. Now one more operation, if we have to take a square root of a complex number. So square root of a complex number. How we perform calculate the square root of a complex number. Suppose z is given as a plus jb. We can write it in the polar form as r at an angle of theta, which is same as r e to the power of j theta. So if we have to compute the square root of this, so how we can do that? Z under root. Now we can do this. Let's use the polar form or Euler's form. So we can write it like this. Now this can be simply written as under root of r at an angle of theta by 2. Now this result comes from de Moivre's theorem. So this is from de Moivre's theorem. Okay, you can check the proof from any book. So we can write it like this. So square root of a complex number also becomes very easy in this polar form or Euler's form. If you use this form, you will see it is very easy. Okay. If you apply square root means 1 by 2 power raised by 1 by 2. So if we have to prove this, so we'll say z under root is same as under root of r e to the power of j theta, which can be written as under root of r and under root of e to the power of j theta, which is same as under root of r under root of this is so whole raised by 1 by 2. When a square root is whole raised by 1 by 2, we can write it as under root of r e to the power of this can be written as like this, which is same in the polar form as under root of r at an angle of theta by 2. So this is the proof. Okay, this is the proof. All right. So simply, if we have to calculate the square root of this complex number, take the square root of this magnitude and divide phase by 2. That will give you the, yes, here is little proof of this. So you can check the proof. So this is the proof. Okay. All right, so let's solve one simple example such that we understand these different types of operations. Let me take a very simple example of this, what we have learned so far. So let's consider a complex number. Okay, let's suppose our complex number is E, which is 10 at an angle of minus 30 plus 3 minus 4j divided by 2 plus 4j and 3 minus 5j conjugate. Okay, star means conjugate. So this is our complex number. Okay, what will be z in simplified form? Okay, now you can see here what we have. We have one part of the complex number is given in polar form, another is given in rectangular form. Then we have to do the addition operation. Similarly, on the denominator side, we have multiplication between two complex numbers, and there is a conjugate operation. Okay. Now, first, since addition becomes very easy in rectangle form, so what we'll do, we'll convert this into rectangle form. So how we do that? We can write it as z is 10 at an angle of -30 plus 3 minus 4j divided by 2 plus 4j and 3 minus 5j conjugate. Now this can be written as 10 at an angle of -30 can be written as 10 cosine of -30 plus j 10 sine of -30. This is the rectangular form of this part, okay, of this polar form. Then plus, then we have one more component, 3 minus 4j divided by 2 plus 4j and 3 minus 5j conjugate. What is the conjugate of 3 minus 5j? 3 plus 5j. Replace j by minus j simply. Okay. Now this can be written as 10 cos minus 30. Cos minus 30 is 0.866, so it will be 8.66. So 10 cos 30 will be 8.66 plus sine 30 is 1 by 2. So minus sine 30 is 1 by 2 or 0.5. So we can multiply it by 10. That will be 5j plus 3 minus 4j. Now the multiplication we can do either in polar form or rectangular form. Here polar rectangle form is given. So let's do the multiplication in rectangle form. So it will be 2 3 is 6 plus 10j, 2 5 is 10 plus 4 3 is 12. That is 12j plus 5 5 is 20 j square. Okay. Now we can write this as, so this is our z. Z is 8.66 plus 3 is 11.66 plus, is this correct? So this should be minus here. Here this should be minus because we have sine of -30. Sine of -30 is minus 0.5 multiplied by 5. 10 is 5. Okay. So 4 minus 4 minus 5j is minus 9j divided by now 6 plus 10 plus 12 is 22j. And j square is -1, so it will be minus 20. So this will be equal to 11.66 minus 9j divided by 6 minus 20 is minus 14 plus 22j. Okay, so this is our complex number. So z will be equal to, so this is the complex number. We have this in rectangle form on the numerator side and rectangle form on the denominator side. So let's convert these into polar form. Okay, so polar form of the numerator side will be 11.66 square plus minus 9 whole square at an angle of tan inverse minus 9 divided by 11.66. Please check the calculations one more time. And this will be on the denominator side. We can write it minus 14 whole square plus 22 square at an angle of tan inverse 22 divided by minus 14. Okay. Now this under root of 11.66 whole square plus 9 square is simply comes out to be 14.73 at an angle of tan inverse minus 9 divided by 11.66 is minus 37.663 divided by so This will be the magnitude of this denominator side will be 26.08 at an angle of tan inverse 22 minus 14. So here the real part of the complex number is negative, so it will be minus 122.47 degrees. Okay. Now the numbers are complex numbers are in polar form, we can do the division. So the division of this will be, if you divide 14.73 by 26.08, then we can write this 37.663 minus 122.47. Okay, simply divide the magnitudes and subtract the phases. That's what we learn here. So 7 division of this will be, and the result is simply 14.73 divided by 26.08 is simply 0.565 at an angle of minus 160.13 degrees. So this is the result in polar form. The result is in polar form. Now you can also convert it into rectangle form. Suppose the answer is given in rectangle form. You can write this as 0.566 cosine of minus 160.13 degrees plus j 0.566 sine of minus 160.13 degrees. Okay, this is the rectangle form. Now compute the cosine of and sine of 116.13 degrees. You will get the answer in rectangle. Okay, so our complex number was something like this. So now the result is here, either in polar form or rectangle form. Now let's consider one more example in order to learn the concepts. Okay, let's consider, let's suppose z is under root of 40 at an angle of 50 degrees plus 20 at an angle of minus 30 degrees. Okay, so this is our complex number. Now what we are given? We are given addition of two complex numbers which are in polar form, and we have to add them, and then we have to take the square root of the result. So first of all, what we'll do, we'll convert the polar forms into rectangular forms. Okay, then we'll add. After addition, we'll convert the result back into polar form and do this square root. I'll perform the square root of that result. Okay, first let's see what is 40 at an angle of 50 in rectangle form equal to, so we can write it as 40 cosine of 50 degrees plus j sine of 50 degrees. Now if you find cosine of 50 degrees plus j sine 50 degrees, you see this is equal to 0.642 plus j 0.766. Please check the calculations one more time yourself. Verify these calculations. So if you multiply 40 with the 0.466, result is 25.72. And if you multiply 40 with 0.766, result is J 30.64. So this part we have converted into the rectangle form. Now we'll convert 20 at an angle of minus 30 degrees. So this can be written as 20 cosine of minus 30 degrees plus j sine of minus 30 degrees. Okay, this can be written as 20 cosine of minus 30 is, I think, 0.866. Please check this calculation one more time. Plus j sine 30 is minus 0.5. Okay, and then multiplying this, we'll get 17.30 minus 10 j 0.5 multiplied by 20 is 10, still minus 10. So now we have converted the two parts of this complex number, that is 20 at an angle of minus 30 is equal to this, and 40 at an angle of this is equal to this. Let's add these two complex numbers first. So we'll do the addition in rectangle form. So 40 at an angle of 50 degrees plus 20 at an angle of minus 30 degrees. Now 40 at an angle of 50 degrees is equal to, that's equal to 25.71 plus J 30.64 plus 20 at an angle of minus 30 is 17.30 minus MJ. Now if we add these real part with real part and imaginary part with imaginary part, we'll get 43.01. Please check the calculations. Then 30, that is 20.64. 30.64 minus 10 is 20.64. So the result is in rectangular form. Now we'll convert back this result into polar form. So we can write it as under root of 43.01 square plus 20.64 square at an angle of tan inverse 20.64 divided by 43.01. Okay. Now, if you calculate this, 43 square plus 24 point square is, please verify the calculations yourself, that is 2277.5905 at an angle of 25.63. Now under root of 20, under root of 2277.5905 is simply equal to 47.724 at an angle of 25.63. So this result, this inside the square root, we have converted into this complex number. Now what we need to calculate z. That's equal to under root of 40 at an angle of 50 plus 20 at an angle of minus 30 degrees. That we have converted into 47.724 at an angle of 20. Then we have to take the square root of this. Now we know how we take the square root of this. Square root of a complex number is simply, if we are given like this at an angle of this, we take the square root of the magnitude and divide the phase by 2. So our R is equal to this. So it will be under root of 47.724 at an angle of 25.63 divided by 2. So that comes out to be equal to how much is under root of 47.724? That is 6.908 at an angle of 25.63 divided by 2 is 12.815. So our complex number simplifies to this. Okay, so this complex number, the square root of this is equal to this. Okay, I hope you have learned the concept. First of all, how do we represent the complex numbers? There are different forms: rectangle form, polar form, and Euler's form. Okay, we can represent a complex number by different forms: rectangle form, polar form, and Euler's form. And we saw the relationship between these, polar form and rectangle form and Euler form. These are summarized here. Then we learn some operations. For example, how do we perform the conjugate we simply replace j by minus j in rectangle form or theta by minus theta in polar form. Okay. If we have to do the addition, addition is usually preferred in rectangle form. That's how we perform the addition. Similarly, subtraction is also preferred in this rectangle form, and this is how we perform the addition. Okay. Then multiplication. If we have to do the multiplication between two complex numbers, and now multiplication becomes very easy in polar form. You can say simply multiplying the magnitudes and adding the phases together. Okay. All right. We can also do the multiplication in rectangle form, but it is a little bit difficult compared to the polar form. Okay. Then division is also very easy in polar form. We simply divide the magnitudes and subtract the phases together. Then we learn some, then square root of a complex number is given by this. Okay. And then we saw proof for this. Then we learn few examples, and this is it. Okay. In the next session, what we'll do, we'll learn what is a phasor. Okay. That means in this session here,